So last time we did the sheet. Yes, sir. What's up? You may. Sure. Everybody else has a copy of that? Anybody else need a copy of that handout from last time? Okay. So we had those 12 grades on a 10 question quiz. So we got the mean was 6.25, right? And we figured out the variance and the standard deviation. I think standard deviation was 2.4. All right. Yeah, 2.491. All right, so that's pretty much where we left it last time. You guys semi with me here? Yes, sir.
What chapter?
This is section 3.3. All right. Blah, blah, blah. Let's skip part C for a second. Part C is the one that asks about how many standard deviations. That's one reason why I was writing these numbers up here. We'll get to that in a minute. Let's do part D real quick, because part D we can do. Part D is a question I like to ask you. I'm going to ask you a question like part D on very many of these tests. So part D says, put the mean found in the middle of the line, the 6.25. If I go up one standard deviation, where do I end up? Yeah, so 6.25 plus 2.5 roughly is like 8.75 almost. And minus 2.5, 3.75. Cool. Let me stop right there. You guys see that? So if I take the mean and I subtract one standard deviation, so I do 6.25 minus one of these, and I do 6.25 plus one of these, that's within one standard deviation of the mean. And let me make sure that you guys, a lot of the theorems and rules and charts we're going to use are going to be built on this idea of, since the standard deviation tells me how spread out the data is, if my data was really spread out, what would the standard deviation do? Would it get bigger or smaller? You get bigger. And if my data was really, really tight, that it didn't spread out much, my standard deviation get really, really, really tiny. So I often call standard deviation steps. So if I have data that's ranging over something and I step through it, my standard deviation is just the right size so I'll see the whole thing, right? If you've ever been traveling across the country and you're going barreling down the road and suddenly the speed limit changes because there's a town coming, and if you blink you miss the town because it's a tiny little town, one stoplight town. You guys, anybody ever road trips? Yes? You know what I'm talking about? So the speed you're going is too big of a step. If you slow down, then you can actually see the town, right? So my standard deviation is going to get bigger if my data is really spread out. It's going to get smaller if my data is not very spread out. So there's kind of a marriage between the amount of data that you see and how many steps out that you take. So if I take one step out, so right now we're just doing this concretely, before we even get to a theorem that talks about this. If I just take one step up and one step down, so one standard deviation up and one standard deviation down, what data points are in between here? So looking back at the data, how many of the data points are in there? So there's, let's see, the data looks like this. 4, 6, 9, 4, 10, 10, 5. Let's do this. Let's circle the ones that are in between. Right, so between like 4 and 8. You guys see that? Would 9 be in here? Hell no. Would 3 be in there? No. So in between 4 and 8. So between 4 and 8. That's a 4 there, Jeff, right? Yeah. 4 and 8, 4 and 8, 4 and 8. So it's like 1, 2, 3, 4, 5, 6, 7, 8. 8 data points are in here, right? Out of how many? 12. Out of 12, what percentage is that? 66.6. Yeah, 66.6. All right. Yeah. Cool. Repeating. So that's interesting. So if I go one step out from the mean, I expect to catch. If I go a couple steps out, I expect to catch some of the data. Because the whole idea is the standard deviation is a measure of how spread out the data is. So if I start at the mean and I start going out so many standard deviations, I should eventually catch a lot of the data, because that's how, on average, how far the data gets away from the mean. But that's all I want you to do on this kind of problem. And then once we start talking about the theorems, I'm going to ask you some follow-up questions to this. But right now, this is just the concrete. I can actually just go to the data and count how much data is in there. All right, so let's go back and talk about part C, and then we'll try to connect those ideas together. So let's say that I had data from 42 to 62, right? You guys kind of with me? And actually, let me do this. Maybe I should do... No, I don't want to use that data. So let's say I'm in a data set where the mean is, let's say 42. And the standard deviation is, what was it, Jeff? 5, I think it was. And the way I did that was, if I start at 42, it takes me about 4 steps to get to 62. So how big is each step? 5 big. Is that cool? That kind of feels like what we did class with. The same kind of math, right? The same kind of physical math. All right, so if I want to say, well, how many steps? So every step is 5 big. So, of course, how many steps away is 47? Yeah, 47 is 1 step away. So you're going to have 1 step and I'm at 47, right? How are we doing so far? All right, that's kind of silly. So I would say that the number of standard deviations from 42 to 47 is 1. It's 1 step away, 1 standard deviation away. All right, that's amazing. So let's try to make a formula out of this, because that was too easy. That was too easy because 5 goes into that evenly. So what if I ask you exactly how many steps away is 59.2? Yeah.
So is 42 supposed to be representing the mean right now?
Yeah, so I'm in the middle of the data. So back here there's 37 and there's other stuff back here.
Right, so
Right.
yeah, okay.
So there's like 37, 32. All right, cool. Right? I like it.
You're only asking for the standard deviation away from the mean, right?
Yeah, so all these theorems, because how did we develop the standard deviation? What was the main idea behind the standard deviation? It's the average distance from the mean to the data points, right? Let me say that again. So when we calculated standard deviation, what was the big chunk of it? X minus X bar. The distance from the mean to the data points. And then we averaged them. So the standard deviation is the average distance from the mean to all the data points. So then all these theorems we're going to talk about will involve how far away from the mean am I? So then you start talking about, well, what's an unusual value? How tall is unusually tall? Well, it depends on how far away from the mean you are. I really want you to see what I'm doing right now. I'm trying to make it very concrete. The idea of distance from the mean. And I like talking about standard deviations as steps, because then you can remember it that way. Don't say steps on the test. Say standard deviations, but steps kind of make sense. I'm stepping around the data. If my data is really small, my steps have got to be so I can actually see the data. If I go, well, I missed the whole damn data, just like I missed the whole damn city. If my data was spread to crazy 0 to 18 billion, I want some big-ass steps to get around there, right? Otherwise, it's going to take me forever to get up to the end of the data. So that's why the standard deviation makes sense to think of as steps, stepping around your data. I was going to say something earlier. I forgot. Shit. Let me see. So let's just finish this out. This very concrete example of what's going on. How far away from 42 is 59.2? Exactly how far away? So can I do it as easily as 47? Because it doesn't. Because what? Why was this 47 easy? Because 5 does what easily? How far apart are these? 5. So they're 5 apart, and how did we get 1? We divided by 5, right? 1 step fits into 5 units exactly perfectly, right? So that's why it was 1 step away. So how far away is 42 to 59.2? Yeah, 59.2 minus 42, right? That's 17.2. Divided by how big each step is to figure out how many steps fit in there. Are you with me? So if I divide by 5, what do you get? Who do I?
3.44.
3.44. And in general, here's the truth. In general, we consider anything that's more than 2, like positive 2 or negative 2, we consider that to be unusual. If you're more than 2 standard deviations away from the mean, that is unusual. So let's bring in some height data, because we kind of know what an unusual height is. Today I was grading papers at Panera, and I saw a little person. And you don't see them very often, right? That's why we consider them, their height's unusual. And your brain just goes, oh, okay. Because we don't see them all the time, right? If I saw somebody that was, if I saw Manute Bol, anybody know who Manute Bol was? He played in the NBA. He was like 7'10" or something crazy. I got off a Southwest flight, and you can't miss him because he's the only dude you can see above the crowd. 7'10" or something crazy. Do I see that all the time? It's unusual. Why is it unusual? Because his height is so many steps above the mean, the middle. How are we doing so far? So a very important concept is, when are things getting weird? When are things getting unusual? Do I need to correct for something? Immediately in my head, I think about nuclear reactors. When is it getting unusual? They get the little readout. How do they figure out where to put the little red spot, so that Homer goes, oh shit, I got to push something, right? They figured that out. They figured out how far away would be unusual enough to go, oh shit, I got to do something. All right, so let's formalize this like we always have to. So let's try to make a formula out of this, and we'll give it a name. And this is going to be basically our life once we get out of chapter 4. 4 is all probability. But let's try to make a formula out of it. What was this 50? Well, let's start with this. What was that 42? So the formula looks like this, starting off. What was the 59.2? Was it anything special? It was a data point, which is x. And if you're looking at your handout, you're starting to see I'm just making the formula that's on there already. And we divided by 5, which was the standard deviation. What we call this is the z-score. Z-scores are stupid important. What kind of sucks is we introduce it now because we're about to get into measures of relative position, like percentiles. If you take the SAT test, they're going to tell you what percentile you scored in. It tells you relative to everybody else where you are. Z-scores are a relative position. So if this was a test and the average is a 42, number one, I'm sorry. Actually, I got like a 22 on a test once in grad school, and the teacher said, good job, because he curved the hell out of it. Nobody got above like a 20-something. Anyway, good thing to know if you're going to grad school. Just expect really low grades and then be told you did a great job. So tell me this, what would the z-score be for 32? You shouldn't have to do any work, but there is one thing you got to realize. How many steps below is it? 2 below, so it'd be negative 2. If you did the formula, what would the formula be? 32 minus 42. So it's going to be negative, isn't it? So then negative just tells you it's below. So if on the quiz you got below the average, which is 75 something, your z-score would have been negative. The higher you were above it, your z-score would have been more and more positive. You guys kind of with it? Yes, sir? You're good? Okay. All right, I like it. Oh, this erases all over the place. All right. This idea of z-score is hugely important. What would this look like? Is this for a sample or a population? How do I know it's for a sample? Because what would be there if it was a population? What's the population mean? Mu. What's the population standard deviation? Fat R, right? Like, I know how to draw, I don't know how to call it. It's lowercase sigma, just say sigma, yeah. Is that cool? They are the same exact damn formula. You just use different labels because you're talking about different kinds of groups. But who cares? They're the same formula. In fact, very few of you will believe me. Because we'll see this z-score formula with different stuff in here, but the z-score formula is never different. It's always our data minus the middle divided by the standard deviation in that situation. Look how I cover my ass. But the z-score formula basically never changes from that. We'll come back to that again. I'm doing a lot of foreshadowing right now, so I think you'll be able to apply this. So let me ask you this question. Let's do this real quick. If there was a test, bless you. So in our test, the average was a 75.3, I think, and the standard deviation was like 14. And let's say you made I don't know, say you made a 71. What would your z-score be? Go ahead and figure that out. Oops, that's X bar. Let's see the stats. So if you have a test, like a quiz, there's 75.3, standard deviation was 14. I want to know if somebody got a 71, what was their z-score? How do you set it up? You notice that the mean is always second. If you get those wrong, you got it on the wrong side. So you should know going in, this is going to be negative. It's below the mean, so you should know it's negative. So if you don't get negative, you know something went wrong. Divided by 14. Do it one more. I'm sorry. 0.307. So we do 3.1. Z-scores will always round to two places, and you'll see why. We're eventually going to use a chart that only goes out to two places. So that's a good reason for that. How are we doing so far? So this person was almost a third of a step below the mean. Do you guys see how I can say that? This is almost a third of a step below the average. Now, these two guys just compared. They said, this guy's in Calc 2, and he said, I got a 59. And this guy's like, I got a 71. Nah. This guy better shut up, because this guy actually did relatively better. What's his z-score? Yeah, it'd be 59 minus 61 over 13. Negative 0.154, something like that. So do you see which one was relatively better? Which one's not as far below the mean? That guy, right? So when you're comparing scores with somebody else, you actually have to take into account what the average was in that other person's class. If you got an 80 and somebody got a 30, they could have actually done relatively better than you if the average in that class was like a 32 or something, right? You guys kind of with me here? That's why on the SAT, has anybody ever taken the SAT or ACT or something like it? They report to you, ACT I think they just give you, I can't remember now, percentiles in the SAT for sure. When you get your results back, they tell you you're in the 80th percentile, right? Which means if you're in the 80th percentile, you scored better than 80% of the people that took that same test. That doesn't mean you got an 80% of the test. The reason they do that is because is the test the same every time? No. And it would be a little evil if they changed it and they happened to make an easier test. What would happen then? If they accidentally made like an easier test, then everybody should do better, but they're still in the relative same position according to the other people. They would still be in the 80th percentile if that's where they were supposed to be. You guys kind of with me? So z-score is sort of like that. It's not affected by, you can compare across things easier. So that's why we do the SAT like that. I can compare across people easier. Maybe. Sort of, kind of. Okay. So on the day you go to take the SAT, just enlist a lot of really not smart people to take it all on the same day as you. All right, that's the thing to do. Oh, I'm sorry. My dean is going to watch that and stay in the chapter. All right. Okay. So I wanted to do that since that was on that little handout, how to get this z-score, right? I didn't even say what that is yet, but that's what it is. So I'll tell you this right now. You ready? A question that's going to be in every single test. And someday, I'll get everybody get it right. But so far, I think normally there's about 10 people that get it wrong at least. You know, I'm telling you, it's going to be on the test. So if I'm going to ask you, what does the z-score tell you? And that's not good enough. Because then I'll be a real dork and I'll say in miles, in light years. Yeah. What does the z-score tell you? It tells you the number of standard deviations from what to what? From the mean to the data point, right? From the mu to the x. I like that. That's pseudo-English. I really don't want you to memorize the wording and all that kind of crap. I want you to just make it make sense. That's all a z-score is. If the z-score is 5, that means that data point is 5 steps above the mean. Holy crap. If that was a height, that dude is tall as hell. That guy's 5 standard deviations above the mean. So let's do height for a second, because that's something we can really imagine easily. See if I remember this roughly. For American men, the average height is 69 inches, and the standard deviation is 2.8 inches. Pretty sure that's those are the last numbers I've seen. There's a lot of variation now, but oh well, we'll just stick with those. And I have to say American men because every culture has differences between their averages, right? Norwegian men are like freaking tall as hell. Somebody, I can't remember. So let me ask you this. Oh, how do I want to say this? So let me give you a couple of heights. Find the z-score for these. If I had somebody who was 62 inches tall, some dude 62 inches tall, and if I had some dude that was, what you got, Jeff? 79 inches tall. Figure out the z-score for both those situations. I mean, my z-score is basically 0, which meant my dreams of being a basketball player were pretty much dead at 15. All right, let's see how this comes out. What's this formula look like when you set it up? 62 minus...
Negative 2.5.
Yeah, negative 2.5. Does that look all right? All right. And this is about 5'2", right? Well, this is 5'2" inches. This would be what? This dude is how tall? 6'7". I like how I'm making the thing and I'm writing the inches down, but I want to do that for me. So is this unusually short? What did I say earlier? Anything outside of how far?
2.
Good. 2 up or 2 down? So anywhere outside of negative 2 to 2 is considered unusual. That doesn't mean anything other than it's not what I expect to see. We expect to see something close to the mean, because most of our data should be close to the mean. Especially because, especially if your distribution, what do we know about heights? I think I already said this before. Heights are normally distributed. And where is most of the data? Close to the mean. So this person would be down here somewhere, where there's not a lot of people. And then the 6'7" person, which in basketball, of course, is not crazy, but if I saw a 6'7" dude, That would be pretty decently tall, right? What's the z-score here? 3.56? 57? Whatever, somewhere in there. So that's definitely unusual. That's more than 3.5 steps above the mean. Holy crap, right? If we did Manute Bowles, which I think he's like 7 foot something. I said 7'10", I don't know if that's really true. But this would be crazy out there, right? So most of us, if we did our own individual, all the men, the women, your average height, if I remember correctly, which actually right now I can't for some reason. 64, something, 65. I think your standard deviation is 2.5. You have to look that up. You can figure out your own z-score. We should all be somewhere between -2 to 2 for the most part. Not all of us. How we doing? Doesn't mean anything bad about you. Doesn't mean anything. Mathematically, it just means it's not what expected to see. Okay. So I want to take a little step back. I wanted to try something new. I don't know if you could tell. I wanted to try something new, so I've never done it this way before. Get you to understand z-scores fully, which is actually in section 3.4, and then I can talk about 3.3 a little bit easier. So we'll see if that's true. I'm hoping it's true. Let's step back to 3.3. 3.3 introduces two really important things, one of which you must totally remember, and the other one you just have to know it exists. And it's actually towards the end of the section. Let me see, do they even do? There it is. Okay, good. All right. And they give it in opposite order, but I'm going to do it in the right order. There was this guy, his name was Chevy Chev. All right. I just call him Chubby Dude. I've never looked up to see if he actually was chubby, but I just call him Chubby Dude instead of Chevy Chev. All right, stay with me now. And this is kind of going back to what we were saying earlier. I love this example. Just deal with me. Let's say there's an alternate universe and we go to their Florida. And let's say that when we go to their Florida, I talk to everybody in Florida and I get all their ages. It's really boring, this alternate. There's nothing to do. So that's what I do. And when I talk to people, I say, how old are you? I'm 2. Okay, you're 2. And how old are you? I'm 87. Okay, you're 87, all right? Or it could have been the other way around. That would have been. So I end up with a distribution. Every time I hit somebody, I put it on a little dot, and there's a lot of people. So it ends up looking like this, roughly. Wow, look at that. Wow. Sorry, Jeff, just deal with it. All right. You guys kind of with me? You understand? So what was kind of weird about that was, what does this mean? There was just nobody there. There was just nobody aged this, which is kind of like our Florida, right? Who's in Florida? Really young people, old people in Boca del Rey, right, or whatever, in the retirement homes, Boca del Vista, right? So the mean would be about right there. Let's say the mean is right there. You with me? The mean is right there. And let's say the standard deviation is this big. Which really actually doesn't make much sense, but I'm just going to do with it because I already drew it up there. Let's just go with it because I want to make a point about so is this a normal set of data? Is this normal? Of course, using our statistics interpretation of the word normal, it's not. Right? Normal would go up and come back down. This goes up really crappy and then goes up again. Holy shit, that's not really normal at all, right? So for any distribution, what I'm about to say is true. It's a little lame at the beginning, but you got to, because it's dealing with every single distribution you can imagine. Here's what's really weird. No matter what numbers you come up with, you make a list of numbers. I don't care what numbers you come up with anything. It will follow the rule I'm about to put up here, which is a little bit freaky. Think about it. So what this dude Chevy Chev said was within, right, English Jeff, within one standard deviation of the mean, there's at least, you ready for ground shaking, 0% of the data. Wow, thanks, Chevy Chev. That's going out on a limb. Right? I mean, what's he saying? Within one step, there could be at least nothing. All right, good job, right? So that certainly kind of matches here. If I go one step up and down, did I catch anybody? No, right? All right. That sounds like Pokemon, but we'll be all right. So the next thing, and here's where things get a little more interesting. Within 2 standard deviations of the mean, there's at least 75% of the data. So if I go one more step up and one more step down, for some reason, now obviously on my picture, and of course I drew the picture, I made it up, so I could just make this happen. If I go one step up and one step down, there's at least 75% of the information. My picture sucks, the scale's off, but screw it. You guys understand the main idea. Now why? Why should that be? I could have drawn this picture differently, couldn't I? Let's say I'm God, and I reach down into alternate universe Florida, and I make everybody older and younger. Rah. I'm just trying to escape the steps, right? The steps are coming to get me. I'm trying to escape. But the minute I do that, what happens to my steps? Rah. If I make my distribution wider, what's my standard deviations do? They get bigger. You can't escape. That's what Chebyshev realized. He says, if I push these apart, these get bigger. They're still going to catch. I can't get into all the math that led to that specific number. You don't want me to. Trust me. I don't care how far you've gone in math. You don't want me to show you the math why in that. But the idea is kind of cool. The idea makes sense, is my hope. If I try to pull them apart to escape, my steps get bigger. They still catch. So no matter, if you make a list of numbers up out of nowhere, just make up a list of numbers. If you calculate the average and the standard deviation, this is true, period. I don't care what your numbers look like. Right? Can't use complex numbers, real numbers. But they could be negative 18 billion, 7, square root of 11.6, your birthday, your favorite number, your cat's age, your cat's favorite number if you talk to them. I don't know. And then the last thing here is within 3, there's at least 89% of the data. Now, I'm almost 100% sure that most of you guys can't quite grasp how freaky this is. What did we do earlier? What did we find on that sheet? We found that within one step there were 66.6, wasn't it? That's definitely at least 0%, right? That's kind of crap. And this at least thing kind of makes it seem less strong. But there's no way to get less than 3/4. There's no way to make a list of data, to find a list of data, to see a list of data, to see anything that doesn't follow this rule. There must be. I really want you to understand this. So watch this. This is kind of cool. If I didn't know that heights were normally distributed, and all right, let me see if I can say this. And I wanted to make sure that why are doors as tall as they are? Why do you think they're as tall as they are? They take into account the average height and they go above that so much so that fewer people have to duck. So, because if a lot of people hit their head, number one, that's stupid. But we live in America where they have to put a little thing saying, do not use the hairdryer in the shower. So, they're not going to say it was your fault that you didn't duck for the damn thing. But they just want to make the door tall enough so only a certain small percentage of people will actually have to duck. Are you guys with me? So to do that, they had to know this. So if I wanted, well, we have to use these numbers right now. But if I wanted 11%, make it 11, Jeff. There you go. If I wanted 11% of all dudes, let me say this a better way. Sorry. If I wanted 5.5%, you'll see where that came from in a second. 5.5% of all dudes would have to duck. And I feel, okay, that's good for PR, that's good. We're not going to get that many complaints. Are you guys kind of with me so far? I want to make my door tall enough so that only 5.5% of men have to duck. All right, now where the hell did I come up with that? Well, let's see. In the middle is 69. Chebyshev says what? He says within 3 steps, there's 89% of the data inside there, right? You guys kind of with me so far? So watch, you're going to do exactly this on some of your homework. You just make this little number line, this little line. If I go 3 steps up, where do I end up? How big is each step? 2.8. So if I go 3 steps up, somebody help me out. 77.4, right? Yep. And if I go 3 steps down, crap, now I got 80s Paul Abdul on the head.
60.6.
Yeah, was it 60.6?
60.6.
60.6? Okay, cool. So that means that in here, there's how much of the data? There's how many men are in there? 89%. Which means how many is below or above that? 11%. Which means how many is higher, taller than that? 77.4. About 5.5. Now, this is not perfect, but I'm just going to go with this. Because they're actually normal anyway. So about 5.5% are up here, I can assume, so I have to make a big assumption, but let's just go with it. So that means I'm going to make my doors at least that tall, if not a little bit taller maybe, to even, does that make sense? Airlines do this all the time. How do you think airlines work with this? And I'm not talking just about butt width, right? So that, as Americans get wider, they're like, do we make them buy another seat or do we make the seats wider? Right? So the whole plane's got to get wider. Yes, sir?
Weigh the luggage, weigh the passengers, average width.
Even something more, what desperately sucks when you go to the airport, something that happens that they might do to people. They have several announcements. We're looking for volunteers. And then they just say, nobody's volunteered, so screw this person and this person. You get bumped, right? And why does that happen? Do they sell exactly the number of tickets that they have seats? Do you know that this is not true? They oversell almost every flight, right? If they can. Why would they do that? Because they know that a certain percentage of people don't come. So they're playing the odds. They're saying, they're doing something like this. They're saying, how many tickets above what we should we sell so that a certain percentage of people would get screwed? And they want to control that percentage, don't they? If this is too high, they got bad PR. They're in the news. News is going, this airline sucks. I mean, it was basically all of them. But you guys, and if it's too low, that means they're not selling enough. How am I going with this? If it's too high, that's bad for them. That's bad PR. And if it's too low of a percentage, no, too low is bad. Screw it. You guys kind of with me? I lost myself. So this is the percentage of people that would be upset. Right? Because this is how many people that would actually show up that actually have a seat and they had to be bumped. So they want to control that percentage. They don't want to sell too few, because then the plane is not full and it's not efficient business sense, right? But if they sell too many customers are upset, they're going to go to the news, bad PR for the airline. So they have to kind of gauge that, see where they want to put it. How are we doing so far? There's actually exactly that problem in the homework later in the course, where we have to figure that out ourselves. Oh, joy. But does that sort of make sense? Developing door heights, figuring out widths of chairs, figuring out how many above to sell airline tickets. They're all kind of based off of this idea. All right, maybe. Yes? If there's 89% in here, what percent is outside? What percent of men is out here? 11, right? The rest? And what's half of 11?
5.5.
5.5, right? Just so you guys know, the assumption I'm making is roughly symmetric, because if it's not symmetric, there might be bigger, more stuff over there. But still, the idea still applies. Okay? I don't want to get into too many details. All right, maybe. So I like this. This is Chevy Chev. This is his rule. He came up with it. Supposedly, he got credit for it. Now here's the one we're going to use most of the time in this class. That's Chevy Chev. That's the one that I want you to know exists, but you don't have to know those numbers. Here's the one we're going to use. It's called the Empirical Rule. And the word empirical actually means... Oh, yes. Oh, that's right. Sure. So the word empirical means by observation. So if you ever hear something about we empirically discovered this. That means they observed something. They poured some acid on it and it did this, and we empirically observed this. All right, good. So it's based off of observations. So the empirical rule is actually when we put into a computer and we said, computer, make every single distribution you can imagine and let's see how it fits. And what we came up with was for a normal, if we said, computer, we have a normal distribution. And what do we know about normal distribution? Normal distribution. Is it symmetric? What's it got to be shaped like?
No.
And a bell is symmetric, right? So the perfect normal, not loose interpretation, remarkably strict interpretation, it must be perfectly symmetric. So a truly normal distribution must be, so pretend like that's pretty decent for me actually. So right here, this would be the mean, this would be the median, and this would be the mode, all three at once. That's in a perfectly normal distribution, that's true. So it cuts it truly in half in every respect that we've looked at. Okay, cool. So is it going to follow Chebyshev's rule? No, not. It still must follow it, but we can be a lot more specific. Now if I go out one step, I know I'm going to catch something. I don't have to say at least 0%. I can be much more specific. So here's what the empirical rule says. How are we doing so far? Are we doing okay? So why Chebyshev makes sense? Because it can look like whatever the hell it wants to. So it could have actually nothing in the middle. So I could catch 0% if I go one step out. But a normal distribution, could that possibly happen? No, most of the stuff is going to be in the middle, right? So here's the one you have to memorize. You have to know these numbers. Oh, shit. When we get to chapter 6, we're going to put this whole process on freaking steroids, and we're going to have this giant chart that tells us not billions, but a lot of values. But right now we're just going to know 3. All right. So just like Chev, this guy's got a lot more, and there's no Mr. Empirical, right? So no. But this rule has got it a little bit easier. It's got to be normal going in. So within one step, within one standard deviation, there must be 68% of the data. Now just to be above boards, it's actually like 68.26 or something. That's an approximate. But it's got to be exactly that, and nothing else around it. It's not at least 0%. It's got to be 68 frickin' percent. How are we doing so far? You're okay, you gotta go. So those grades we did earlier on that handout, what did we find within one step, within one standard deviation? How much of the data did we find? 66.66, right? Isn't that close to 68? So maybe that's loosely normal, right? That could possibly be loosely normal. Let's go, what about within 2? Within 2 steps, there must be 95% of the data. And now you see why maybe we call 2 standard deviations away outside of that as unusual. If 95% of the data is inside of 2 standard deviations, what percentage is outside? So the chances, the probability that something happens outside of 2 steps, outside of 2 standard deviations, is a 5% chance. I think that's a good number to use as an unusual occurrence, right? Later in the class, when we get to chapter 8, we'll actually be able to vary that number, that 2 steps. But for the first part of the class, when they say find the min and max expected values, or they say is this unusual or is this usual, they mean within 2 steps. If the z-score is 2.8, that's unusual. If the z-score is negative 1.4, that's usual. Nothing weird. Nothing to see here. Move on. So what about within 3? There's no pattern here really, so don't try. Within 3, there's 99.7% of the data. So basically, if you go out 3 steps, you have caught just about everybody. There's only 0.3% outside of there. This isn't a perfect normal distribution. Most things aren't perfect, of course. But in math, we always start with perfect, and then we screw with it a little bit to make it work. All right, baby. You guys are doing a good job of pretending to be awake. I like that. All right. So on the problems in the homework, if they ask you, this is a normal distribution, what percentage of the data would be between these two? All you do is you make that line like we did and see how many steps that is. So if I had a mean of 10 and a standard deviation of 2, and I said it was normal, what percentage is between, what you got, Jeff? 6 and 14. Well, here's 10. If I go up a step, that's 12. If I go up another step, that's 14, right? Down a step, down a step. So this is 0. Do you see what these numbers are below? What are those numbers are right below? Be more specific. Those are the what? So what is that tells me the number of standard deviations from the mean to the data point? That is the z-scores. These are z-scores. I love it. You guys kind of with me? See how they come back? Ooh. And now they tell me, so now how many steps out am I from 10 for this? 2 steps up and down. And what does this say? There must be how much of the data? 95%. So if I know it's normal, I know a shitload of stuff about it. I know exactly what percentages are in places. It is perfectly symmetric. So how much is outside? Yeah, definitely 5% outside. Earlier I had to do some finagling, but this is definite. This is symmetric, so I know that it's the same on each side. Right? This is 5% outside, so there must be 2.5% up there and so forth. Maybe. There's a really good picture on page 104 in the book that breaks down the normal distribution for the empirical rule. Really good to go to. Okay. We're gonna go all the way through today, man. I spoiled you guys before letting you out early. It's too damn bad. Here we go. All right. So, any questions on that? Yes, ma'am.
Is the standard deviation ever going to be -1 or above 3, or is it always going to be 1, 2, or 3?
All right. So the standard deviation itself could never be negative, right? So you mean like the z-score?
Not really. Well, yeah. Okay.
These numbers here?
No, like this, like in the equation, like will it ever be like? Well, because you said it could either be 1, 2, or 3. Will it ever be over 3?
No, so I want you to understand. There's a lot more in between each of these. So if I know is normal, I should know exactly how much is between -2.1 and 0.49. And once we get to chapter 6, we'll be able to exactly say what percentage is in there. For what we know right now, I can't say shit about that. I can only handle if it's 1, 2, or 3 steps away. You with me?
No, yeah.
But we're going to build on this once we get to chapter 6. I like it. You're like, calm down, dude. It makes sense. All right. All right.
So will it ever be more than 2? That's what you're saying?
Oh, hell yeah. A z-score could be 18. That would mean, if it was height.
So the standard deviation is technically the z-score itself.
No, be
Not
careful.
Well, that's what you asked.
The number of steps.
Yeah.
So the standard deviation here is always 2. That's why I use 2 to build these. And z-score is how many of these it takes to get from there to there. So I like to say it like this. Standard deviation, when you calculate the standard deviation, you figure out where to put the tick marks on a ruler. So if your standard deviation was 8 kilometers, your ruler is giant. You're talking about average distance cities are from the middle of America or something. You kind of with me? Does that make sense? If my standard deviation is 8 kilometers, I must be talking about cities, how distributed they are. You with me? No. So if my standard deviation was 2 feet, then I might be talking about how spread out you guys are from each other or something like that. Right? You're each about 2 feet away from each other, right? Sometimes a little closer, a little further. All right. But the average distance between people. So if that tells me how to set up my tick marks on a ruler. I love this idea. Hopefully you guys are going to be with me eventually. So if I wanted to say how many steps, how many standard deviations is from you to you, I can lay that ruler down and actually take a measurement and see the number of steps between you two. That's the z-score. So z-score, standard deviation is setting up the ruler. How far are my tick marks? So if my data was really stupid tiny, really tight, a lot of it in between 0.1 and 0.1000001, holy shit, my tick marks would be lay my little ruler down, right? But if it went from here to here, maybe this dude will work, right? Maybe this is a standard deviation. And then when I lay it down and I read it off, that's the z-score. That's the connection. So the S is the tick marks on the ruler. Z is me reading off how many tick marks, reading off from the ruler. And that's why, now, if you're going to measure how tall somebody is, you'll use inches or feet. If you're going to measure how far apart 2 towns are, we'll use miles or kilometers, depending on which country you're in. You with me? So that's why standard deviation changes based on the data. It changes the same way that we go from inches to feet to miles. Same reason. To light years. We can talk about distance between stars. Yes, ma'am.
Is ratio ever going to come into factor?
Say again?
Ratio? Are we ever going to use it in this, like ratio?
Oh, ratio?
Yeah.
So the whole nominal interval ordinal ratio, it'll come up every now and again because it's if it's nominal data, I can't do a lot of this stuff with it, right? I wouldn't be able to say my data is BMW and Hyundai, and what's the average and what's the standard deviation, and right? Is that what you're saying?
And then, like, you know how, like, in between 10 and 12, you could say, like, 2 to 1, and then 10 and 12, you could say 2 and 4, to the ratio in between them?
Oh,
Are we going to...
no, because z-score is a pure number of these. So it's not really a percentage of them or something like that, right? Okay. I thought for a minute you meant, like, what if it was 10.7? Well, we can still get a z-score, but we can't use this for it, right? Because then it's not a 1, 2, or 3. Okay. So my dreams are dying in front of me. But it's okay. I had a dream that we could get through 3, 4. Let me see what happens. So let me just do this little piece of it, and then we'll head out. I got to give you guys a practice test. I was talking earlier about SAT scores and percentiles. And if I'm in the 80th percentile, what does that really mean? Good. So if, let me do one thing with you guys and then we'll head out. This is like section 3.4. I got to think about whether or not I'm going to make that do. Let's see. 5, 6, 7, 8, 9, 10. Good job, Jeff. So there's 10 numbers up there, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good job, Jeff. Can somebody tell me your guess as to which number is in the 80th percentile? Which number is in the 80th percentile? And we're going to use this symbol. You know math people, we don't like to write that much. Most of us write like me. So I got some people saying 20. Anybody else think anything different? So if you're supposed to score above 80% of the people, how much whoever this is, how many people do they score higher than? 1, 2, 3, 4, 5, 6, 7. So if you think it's 23, let me tell you why you're wrong. Because if you're supposed to score above 80% of the people, how many people should score above you? 20%, right? And there's only 1 out of 10. There's only 10% above you. So where is the 80th percentile then? In between those two, what does it sound like that we've done before? Something that's in between two. The median. How do you think the median relates to percentiles? If you make the median score, you scored above what percent? The median's always where? In the very middle. So either it's there, so you scored above half, or it's there, so you scored above half. So the median is the 50th percentile. So if you think about it, that only makes sense. It cuts my data in half. It's right in the middle. So to find the 80th percentile, both of these are wrong. Both of these are wrong. They don't have the right percentages. So the right for P80, it's got to be in the middle of these two. And let me show you the math that gets you there, and that'll be it for today. Right? I love that the other class is so used to us getting out early. They're like, "What the hell? You're still in there? What the hell?" So are you ready? It's a 2-step process to find any percentile. 2-step process to find any percentile. Number 1, you take the percentage of how many data points you got. Now I made this a nice list. I made it 10 so we can talk about it. So in this case, I would take 80% of 10. And what does it come out to be? So if I wanted P33, I would take 33% of 10, right? You guys understand this is how, so the first step is, whatever the percentile is, take that percentage of how long your list is. Why is this 10? Because my list has 10. It's not always 10, right? So if my list was 28 long, this would be 28. Good. So don't always use 10. Sounds like it's happened to me before. So what is 80% of 10? 8. So if it comes out to a whole number, this should also sound familiar. You don't take the 8th number. Remember, that was wrong. If it comes out to a whole number, you average that one with the next one. Average the 8th and 9th. if it comes out to anything, so the second step would be do that. First step is, where's the answer? Second step is, go get the answer. So the 8th and 9th are these two. What's the answer then? What's P80? The average of these two. 21.5. Kick-ass. So if it comes out to anything else, it's not a whole number, you round up. So how would I find P33? What would I do first step? 33% of 10. Right? You take 33% of how long the list is. So what's 33% of 10? 3.3. If it comes out to anything that's not whole, anything, you round it up. So then the answer would be the fourth number. So what's the fourth number? 12. That's how you calculate percentiles. My God. That's as much as I can cram in. I'm probably not... Good Lord. I'm probably not going to officially make 3-4 do. I just, for some reason, had to do this before I let you go. So let me tell you this. When you get this 1G is a question from section 3-4, you do not have to worry about that. So when you get there and it says create a box plot, we haven't done it yet. We'll do it for the next step. Yes?
I think for the 80% how you have to put the average of the 36.
Because it didn't come out to a whole number when I did the percentage. So for the median, 50% of 5 is 2.5. Then I would round to the third. Is the third one 1, 2, 3? The third number was either 1, right? But 50% of 4 is 2. But after average, the second and third, you get to right. So the median is exactly a good representation of why that process works. And real quick, you don't have to do this at all if you don't want to. I'm going to have the answer to this on Wednesday. So you don't have to do this at all if you don't want to. This is just what the test have on it, these concepts.
But it's already broken because I did that stuff.
Don't forget to give back my calculators. Don't stretch my budget. It's not the median of I think the median of 5 numbers, half of 5 is 2.5. But I go for 30. Whole number and average. Thursday.
Yeah, I'm pretty.
Yes.
Unless I have my internship starts up on like some days.
Yeah.
But that's mostly. I'm out of class at 12.
Really didn't get through.
I actually try and go because I have my
Yeah, I'll well.
Yeah.
Most likely what I'll do is, I'm just going to go try to find a good spot.
Okay, sure. You can do that.
Yeah, I've already finished chapter 2, so I gotta do all.
No. You could just pick up where you left off in the online. As long as I see it somewhere, you're okay.
Oh,
And just do the rest online if you want to. Does that make sense? If you've already got it on paper, you don't have to do it again online.
oh, I've already finished chapter 1 and chapter 2.
Good. So don't do that online. Oh, you mean you've already done that online?
No.
You've already turned it in. You don't have to do it also online.
Okay, so do I need any code to?
Yes, you do. And the instructions.